Hi, my name is Maisie Anderson, and here is my Physics Lab 4 on the magnetic field of bar magnets. So firstly, what is the purpose of this lab? The purpose is to measure the distance dependence of the magnetic field due to a small bar magnet and compare the measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. The experimental model was using a bar magnet in the lab and using a magnetometer from our phones. Our computational model was on GlowScript, and just as a brief preview of our results, we found that the magnetic field decreases with increased distance from the magnet. Points on the parallel axis experienced a twice as strong magnetic field than points on the perpendicular axis to the magnet when they were the same distance away. And n was determined to be negative 1.2657, k was 8.073 times 10 to the negative 6, and mu was equal to 4.773. So fundamental concepts relating to this lab are the magnetic field versus the distance. So the magnitude of the B field for the bar magnet is equal to kr to the power of n. The natural log of the magnitude in the x direction is equal to the natural log of k plus n ln r. The formula for the on-axis B field is given here, and then the Biot-Savart law is also shown below. So our initial conditions, the system was the phone and the magnetometer, and then the surroundings were the bar magnet and the earth. So our experimental design, in a very simplified overview, was first to determine the magnetometer chip's location within the cell phone, and then by keeping the magnet in the same place, we moved the phone around to find the distances from the magnet, at which point the Bx value was equal to 20 UT, 70 UT, 120 UT, 170 UT, and 220 UT. We also found a distance d perpendicular where B net was equal to 100 UT and recorded that distance, as well as the exact values for the magnetic field at that distance. We determined the x, y, and z components of the net magnetic field at that distance, like I just said, and we corrected the y component and calculated B net for this situation, and then repeated everything 3 times and calculated averages. And then here's just a photo of one of the measurements that we were doing. So here are all of our results from the experimental model, just laid out in one single graph. And from that graph that was shown, we determined n from the slope of that line and found n to be negative 1.2657, and then the y-intercept of that line was equal to ln k, so we determined k was equal to 8.073 times 10 to the negative 6, and then using the magnitude of the bar magnet's electric field, the equation kr to the power of n equals mu naught over 4 pi times 2 mu over r cubed. We found that mu is equal to 4.773. And we observed that when the magnetometer gets closer to the bar magnet, the x component of the magnetic field increases, and the x component of the magnetic field will be close to 0 when it is very far away from the bar magnet. And then here's the code that I use for my computational model. I have my edits of the starter code shown here. And here was our results from the GlowScript model, shown on the right, and then just to compare our computational and observational results, the off-axis B field observed was negative 1.17 times e to the negative 5, 1.63 e to the negative 5, and negative 2.527 e to the negative 5, and the observed B net was 9.857 e to the negative 5. On the other hand, the computational B field was 9.529 e to the negative 6, 2.859 e to the negative 5, 0, and the computational B net was 3.014 e to the negative 5. So there were differences, and these may have been due to measurement inconsistencies, too much movement of the phone while recording measurements, or nearby electronic devices producing other magnetic fields that messed with ours. And for discussion, what if you hadn't oriented your experiment to compensate for magnetic north? the x component of the magnetic field would change, which would then change the values of n and k and create a greater difference between the experimental and computational results. And what if you were to stick two identical magnets together end to end? The magnitude of the magnetic field would double, but there would be no change in the direction of the magnetic field, and this is simply due to superposition. Thank you.